Hi, this talk is on traffic engineering in Microsoft's unified network. My name is Umesh, and I'm coming to you from our offices in Mountain View. Somesh, my colleague, will be in the live Q&A, so please check that out. Microsoft's unified network, OneWAN, encircles the globe. It connects over 60 Azure regions and 190 edge points of presence. A region contains many data centers, and an edge POP is where our network connects to other networks. Wide area networks use traffic engineering to achieve better performance than default routing. Performance can mean maximizing throughput, minimizing utilization, or any characteristic important to the users. About a decade ago, cloud operators found that they could use software controllers and achieve better performance than RSVP-TE. We all built separate networks dedicated for inter-datacenter traffic, which was the fastest growing traffic at the time. Microsoft Swan, Google B4, and Meta Express Backbone are examples of such networks. Segment routing came along, and EBB makes use of it in its network. Similarly, traffic engineering between networks is done by software controllers like ITE by Microsoft, Edge Fabric, and Espresso. Microsoft's unified network uses OneWAN TE inside the network and ITE between networks. Let's look at the Two-WAN architecture. Regional gateways connect the data centers in the region and also contain Swan and core routers that provide long-haul connections to other regions and edge POPs. Inter-Datacenter traffic flows over Swan. Edge POPs only contain core routers, and internet traffic flows over core. Swan uses SDN traffic engineering, and core uses RSVP traffic engineering. Swan uses global knowledge and achieves much better performance. It can time shift less important traffic and decrease congestion. Not only did this improve the SLO of internet traffic on core, Swan evolved to carry mission-critical customer workloads with high SLO. We developed Blast Shield, which allowed us to do global traffic engineering without global blast radius. But the Two-WAN architecture has some headwinds. Internet traffic is growing faster than inter-datacenter traffic since 2020. At the same time, RSVP-TE is reaching its scale limits because of the size of core. Two-WANs require additional devices and power inside regional gateways. There can be times when one network is underutilized and other network is overutilized, and we cannot freely use the capacity of both networks. So that is the motivation for OneWAN. But traffic engineering a unified network is much harder than an inter-datacenter network. For one, the controllers have to contend with 10 times more devices and routes. RSVP-TE is very good in fast reroute, and applications depend on that. With Swan, we had the luxury of building a new network from scratch. But OneWAN has to be an in-place conversion of Swan and core, because otherwise the costs would be astronomical. We connected Swan and core using core's aggregation routers, shown by those blue lines. Then we merged the ISIS domains of the two networks into one. And finally, we remove the extra aggregation layer. The figure on the right shows our new OneWAN sites. Notice there is no Swan or core. It is simply OneWAN. Swan and core backbone routers are what we call small TCAM routers. They can hold some routes, but not the full internet routing table. This is a common practice used in networks to make them more efficient. Now, I would like to highlight 3 aspects of OneWAN's design. OneWAN routing occurs in 3 parts. Aggregation routers are shown in blue, backbone routers in gray, and edge routers in black. Edge and aggregation routers exchange routes using BGP. We assign a site label for every site. The controller injects routes into the source aggregation router to prepend the site label to the packet. This way, the next router, which is the backbone router, can determine the path through the network purely using the site label. This is called traffic steering. The controller also adds a second label, which is the node segment identifier of the destination aggregation router. Anytime we want traffic to use ISIS routes, such as in a fallback scenario, we simply pop the site label and traffic uses segment routing. The second part of the packet's journey is called traffic engineering. The controller creates tunnels between sites and assigns a path label for each tunnel. It also programs all the intermediate routers. Once the packet reaches the destination site, it follows standard protocol routing within the site. Traffic splitting is how flows are hashed to tunnels. The controller selects tunnel weights to achieve a specific load distribution. Note that packets of the same flow hash to the same tunnel, so they reach the destination in order. We split traffic twice, once at the source aggregation router and a second time at the source backbone router. The backbone router can also select different tunnels based on forwarding class. It can send discretionary traffic on underutilized paths to decrease congestion drops. Anytime a tunnel goes down, an agent running on the router changes the tunnel weights in fixed ways. This is called local repair. To make local repair more resilient, the controller gives the agent additional backup tunnels to use should all primary tunnels go down. All aggregation and backbone routers in OneWAN run an agent. The 2 jobs of the agent are to program routes given to it by the controller and to perform local repair. Even though the controller is far from the network device, the agent can react quickly to faults and repair the routes. The controller and agent do not use any routing protocol, just direct communication. The OneWAN agent runs on multiple firmware operating systems, including Sonic. Most of the complexity is in the platform-independent layer. The platform-dependent portion uses firmware-specific APIs, such as gRPC messages to local endpoints in the router and BFD session setup messages. To summarize, we use traffic steering so that we can use small TCAM backbone routers and decrease the scale requirements for TE optimization. OneWAN local repair happens at the tunnel head end, and backup tunnels are ready for use, so it's a fast switchover. Now, migrating from two WANs to one WAN in a live network is like changing an aircraft engine while it's flying. We used new blast shield slices for OneWAN controllers, and we gradually stepped down the RSVP bandwidth to match the traffic migrated to OneWAN. Now, let's look at internet traffic engineering. Our edge POPs contain peering routers that peer with internet service providers. They also contain ExpressRoute devices which allow users to connect to the Azure cloud over private connections. Aggregation routers in the edge POP backhaul traffic to regional gateways. Now, BGP is not performance aware. This can lead to congestion in the peering and backhaul links, and more generally, result in lower quality of experience for users. The ITE controller mitigates congestion and improves the latency and availability of routes. It can perform other functions as well. It can mitigate DDoS attacks and route hijacks and allow users to bring their own IP into Azure. For input, the ITE controller uses streaming telemetry for various interface statistics, IPFix for finding top flows, BMP for finding alternate paths, and map of the internet for measuring latency and availability on alternate paths. Let's look at how ITE mitigates congestion. It detects high drops and high utilization in peering and backhaul links, and then identifies the top flows using the congested link. It looks for alternate links, preferably in the same POP, but if they are not available, looks for the alternate links in other POPs in the same geography. ITE performs the move by injecting BGP routes or routing policy updates. Now, the ITE and OneWAN controllers do not directly communicate with each other, but ITE checks for safety before moving flows, and OneWAN adapts to the change in demand. 70% of ITE mitigations are for egress congestion mitigation, which is traffic leaving our network bound to other networks. And 95% of mitigations are for peering link congestion, though we also sometimes use it for backhaul links. So in summary, OneWAN is Microsoft's unified backbone. OneWAN traffic engineering has given us significant CapEx and OpEx savings compared to Two-WAN. And the new applications we are carrying on OneWAN make SD and TE very exciting. Thank you.